All right, so what we're going to do is section 4.2, Riemann sums, okay? I know in your book they might call it area approximations and stuff like that. Integration is basically a way to find area underneath a curve, okay? So when we integrate, another thing we can say that we're doing is finding the area under the curve, okay? So a mathematician, Riemann, created a couple ways that we could do this using what's called the left, the right, the midpoint approximations, and also the trapezoid method was created after, okay? So here's the idea. So I'm going to show you one example, one big example to help you understand how to do this. Okay, so it's going to take a little bit of time. But again, the idea is basically this. Let me draw this out really quick. He basically said, if I had a graph and someone asked me to figure out the integral from A to B, let's say here's B, then all I'm really trying to do is figure out the area found underneath the curve, this part right here. If he could figure out how much area is underneath that curve, then he said that's basically the same as doing the integral. Now this was before, we found different methods to do this, but that was his idea. He said, look, I got to figure out a way where I can do this. Now, there's no perfect shape. A lot of times there's no perfect shape that'll fit inside of a curve like in that area right there. So one thing he did is he said, well, maybe what I'll do is I'm going to create these rectangles. By the way, don't draw these rectangles, okay? Don't draw them yet. So I'm going to create these rectangles, and by finding out these rectangles area, so just kind of watch, don't draw this out because I'm going to change this picture right now. By finding out the area of those rectangles, I can get an approximate area under that curve. Do you guys understand that? So, but would that approximation be a good approximation? No, would it be an over or an under approximation? Under, right? So he said, okay, well, that's an under approximation. So maybe a left-hand method wouldn't work so nicely. But what if, by the way, this is called a left-hand method because if you look at the rectangles, you see how the top left corner touches the graph? Okay, so if I zoom in a little bit, notice the top left corner of the rectangles will touch the graph. Okay, so he said, okay, maybe I can't do that, but let me get rid of this. It says maybe I do a right-hand method where there's a rectangle that'll touch on the right side of it. Would that be a good approximation? Well, I mean, it covers all the yellow, correct? But it also kind of takes a little bit extra, right? So that would be considered an over approximation. Now, I'm not saying that the left end method or the right end method is better one way or the other. It kind of depends on the graph. Sometimes the left hand method is under the graph. Sometimes it's over. It kind of depends on the graph. Okay. So he looked at it and says, well, that may not be good. So maybe there's another way to do it. So I'm just trying to show you all the methods right now, okay, before we actually go into this. So he said, what about if I develop a method where the middle of the rectangle is touching the graph? Okay, so the middle of the rectangle is right on the graph. Would that give me a better approximation, right? So what do you guys think? What about if the middle is touching? Would that be better? Yeah, right, because there's a little bit over, but there's a little bit under. So maybe when you over approximate it, then you also under approximate it on one side. So maybe they kind of cancel each other out. It all depends on the curve. But, you know, that's one other way that he thought. Like maybe there's a midpoint. So these are all things we're going to learn. He also said, okay, what about, I'm wondering why these won't erase. Why aren't these erasing? I'm going to have to do this. I'm going to have to color this again, sorry. Because the other one wouldn't erase. So then they said, well, what about a trapezoid method? So what if I were to create trapezoids inside? I'm going to kind of exaggerate this one, but trapezoids that kind of fit close to the graph. Does that look like that would be a pretty decent way of doing it? Yeah, right? Midpoint trapezoid are actually some of the best ways to do it. Okay. Left and right, usually you end up either over or under approximating. But you do have to know them, even though they're not the best methods, because sometimes on the AP exams they'll say take a left hand approximation, take a right hand approximation. So you have to know how to do all that stuff. So this is basically what Riemann was thinking. Like, there has to be a way that I can figure this out. And then he said, well, if I could draw these pictures, then I can do this geometrically, right? I can say, oh, I know the area of a trapezoid. I know the area of a rectangle, so I can do it that way. But here are some of the things that I kind of want to go over with you, okay? First off, like I said, I'm going to show you one example, okay? And then I'm going to teach you the equations and everything as we do it. I'm going to teach you the definitions as we do it. So this is just example number one, okay? This is the only example we're going to work on. It does have 4 parts to it, all right? So we're going to find the approximation of the area under the curve of, by the way, I say curve, but they can be lines, okay? And here's the thing, y equals 3x minus 4. They say from 2 to 5. And then they write n equal 4. Now what n equals 4 is, they're saying, I want 4 of these shapes, 4 rectangles, 4 trapezoids, whatever, but there has to be 4 of them. So if they say n equals 6, that means they want 6 pieces to be put in there. Now, understand that the more rectangles you fit into these things, the better your approximation. Does that make sense? Because if I were to have like an area, let's say the area looked like this. If I say, well, I'm only going to approximate it with 1 rectangle, is that a good approximation? Probably not, right? So what we say is, well, maybe if we try 2. Well, that's better. But what if I were to try like 10? Well, I would say like, okay, 1, 2, 3, 4. So you can see there's a lot less space being taken out, right? But there's a lot less space. So the more things you fit in, the better your approximation. Okay? Well, if the more shapes give me a better approximation, then what should I keep doing? If 5 shapes work, what should I do? Maybe try 6, maybe try 7, maybe try 10, maybe try 100, try 1,000, try 1,000,000. Well, using that idea, maybe I should fit an infinite number of them, right? And that's when integration kind of comes in, because infinite numbers, integration basically says that we'll fill it in for you, okay? But let's get to this problem. Now, we're going to find the area under the curve of that function in 4 different ways, okay? We're going to use the left-hand approximation, use the right-hand approximation, use the midpoint approximation, and then we're going to use the trapezoid. Now, just so we could see it, let's go ahead and draw this thing here. Um, this graph, we're just going to draw a quick sketch. I don't need it to be perfect, but we just want to draw a quick sketch. This graph is going to look kind of like this. Let's assume that this is 2, and we'll assume that this is 5. It's going to kind of go something like this. And we're trying to figure out this area right here. Okay? Now, by the way, what we're doing right now, there is a better shortcut. That's called definite integration. That's what we want to get to eventually. Okay, that's the next section. But we're learning how to do it the way they actually used to do this stuff. And actually, there are some places that still do this. That when they were trying to figure out the total area of Hearst Castle, they actually used a satellite to figure out the boundaries and then filled it in with using a computer. They had it fill it in with a bunch of different Riemann sums to find the total area of that section. So they still use this today, but it's a lot less common because nowadays we just use definite integrals. So here we go. What does it look like to do part A? So part A, left hand approximation. So in this one, I'm going to define everything for you guys, okay? And then I won't define everything in the other ones unless I have to. But the left-hand approximation has this formula. It's the integral from a to b of f of x dx is approximately, so here's your formula, b minus a over n times y sub 0 plus y sub 1 plus y sub 2 plus etc. all the way till you get to y sub n minus 1. Notice A and B are our upper and lower bounds. B is the upper bound, A is the lower bound. Okay, n is the number of equal subintervals. So let me write this down. So where n is the number of equal subintervals. In other words, the number of shapes. Okay, super important for Riemann sums. Equal subintervals. In other words, each one of these shapes has the same base. The base doesn't change. You're going to notice on the AP test, they're all different. So there's a different way to do the ones on the AP. It's actually easier. But for Riemann sums, they're all equal subintervals. That means their bases are all the same. Okay? So don't forget about that. B is the upper bound. In other words, the right edge of this, right? Look at the graph. From 2 to 5, I have 2 on the left, 5 on the right. So B is the upper bound, in other words, the right side of it. And A is the lower bound. Okay? Now, this belongs to the integral. So of the integral. The stuff we wrote in the very beginning, right? Integral from a to b of f of x dx. So a and b are the subintervals. The upper and lower bounds. Now, b minus a over n, that part that says b minus a over n, this is the base of these rectangles. So this represents the base of the rectangles. So if you want to figure out what is the size of the base of the rectangles, you do b minus a over n. Okay? Now when we do trapezoids, it's actually going to be b minus a over 2n, and that doesn't represent the base of it. That actually represents the height of it. But we'll talk about that later. But b minus a over n represents the base of the rectangles. So Knowing this and knowing that formula up there, okay? So if I can, let me see if I can do this. I'm gonna maybe keep this in memory because I may have to rewrite it later, so we'll see. So let's go ahead and start this problem, okay? So according to what they gave me, they said they want me to find the area. So here we go. The area from 2 to 5 of 3x minus 4 dx is approximately, notice I'm just filling in the information. They said the integral from a to b of f of x dx, so I put it in there, from 2 to 5 of 3x minus 4 dx is, now notice I'm not going to integrate at all, okay? That's just the way you start writing it. I have to use that formula up there. So b minus a over n. B is 5, A is 2, N is 4. Okay, so B minus A over N. And let me just leave the y sub 0 plus y sub 1 plus y sub 2 plus y sub 3. And that's where I'm going to stop. Now, why do I stop at 3? According to my equation, I'm supposed to go all the way up to y sub n minus 1, right? And if n is 4, then 4 minus 1 is 3. So I have to stop at 3. But we won't worry about the y calculations right now. Let's actually just simplify this. 3 over 4 times y sub 0 plus y sub 1 plus y sub 2 plus y sub 3. By the way, do you guys know what the y values are? Do you understand what these are? Let me go back up to the top picture, if I can. So just to kind of draw a little bit, I'm doing the left-hand method right now, okay? So this is what it's supposed to look like, kind of. Y sub 0 is the left side height of the rectangle. Okay, this piece right here, let me use red. This piece right there, that's y sub 0. This is y sub 1. Y sub 2 is this height right there. That's y sub 2. Y sub 3 is that height right there. Okay, and y sub 4 would be this height over here. But does that height represent a left side to a rectangle? No. But would that represent possibly the right side? Yeah, if I kind of cut it, whoops. If I cut it short, okay, and kind of stop it right there, I could say that could represent a right side of it, okay? But notice I'm not doing right hand side, I'm doing left hand side. That's why y sub 4 does not get used. Okay, so how do I figure out y sub 0? Well, if I know the x value for that line, I can plug it into the equation and I can find the height of that line. Okay, so if I want to figure out what this is, I know x equals 2 there, right? So if I just plug it into the equation, I get 6 minus 4, so that height would be 2. That would be my y sub 0. Okay, but here's the big thing. What is this x value? So that's where the base comes in. So this is where we're going to do a little bit more work. So let me go back. Do you guys understand how I find the heights? So get my x value, and then I'm going to plug it into my main equation. Okay, and that's how I find the heights. So as long as I know my x value, I can find a height to anything, right? I can find a specific point. So this is how I'm going to do it. So right now we have it set up where just the base is identified, okay? So to find, let me write this down here for you guys. To find y sub 0, y sub 1, y sub 2, etc. I'm even going to put all the way up to y sub n because you're going to have to do n at some point. Okay. We're going to use our base. We use our base and add it to our lower bound. Okay, and then I'm going to say keep doing this until you reach your upper bound. So to find your y values, you're going to start with your lower bound and keep adding your base. Okay, keep adding your base. What's my base again? What's the value of the base? 3/4, right? So we're going to keep adding that. I'm going to give you just a minute to finish writing that out. Because guys, once we do this part, the rest of the left, right, and trapezoid stuff is easy. The midpoint is a bit of a pain. Nobody really likes the midpoint method, to be honest with you. But it is really good, but it's kind of like, oh, now I got to find a midpoint between this, and you got to do some more calculations. But usually when you do these calculations once, you can figure out trapezoid methods, left and right, and then midpoint is a bit of an issue. So we will do the midpoint method last, okay, just so you know, because I don't like doing it personally. But it's not that it's hard. It's just like, oh, I got to do more work. So is everybody okay and caught up? Yeah? All right, so here we go. Let's start with our lower number, okay? So y sub 0 is going to be 2. Okay? So what I'm going to do, so I'm going to kind of put a little circle around here. I'm going to add my base. Whoops. I should probably do that on the next one. Let me put y sub 1 right here. I'm going to get my base and I'm going to add it 3/4. Okay, what's 2 plus 3/4? Well, I'll give you the answer just so you guys don't have to worry about struggling. That's 11/4. Okay, because it's 8 plus 3, that's 11/4. So 11/4. Okay, so I'll write it right here, 11/4. That's what goes in that y sub 1, 11/4. Now keep adding 3/4. So 11/4 plus 3/4, that's 14/4. So that's y sub 2, 14/4. Now add 3/4 again. Remember, I'm going to keep doing this until I get what number? They say keep doing this until you reach your upper bound. What's my upper bound? 5, right? So I need to get a 5. Once I get to 5, then I can stop. So I add 3/4 and I get 17/4. So y sub 3 is 17/4. Is this hard to do? No, right? It's not that bad. But I'm not done. I have to get 5. So I'm going to add 3/4 and I get 20/4. What's 20/4? That's 5. So I stop there. Notice I did actually reduce that one because that kind of tells me stop. So notice from 2 to 11/4, that's one triangle. I'm sorry, one rectangle. From 11/4 to 14/4, that's another triangle. I keep saying triangle, rectangle. From 14/4 to 17/4, that's another rectangle. That's 3 of them so far. And from 17/4 to 5, that's the 4th one. And how many was I supposed to build? 4 of them, right? N equals 4. So I have 4 of them. So this is what I'm going to do. You see the y sub 0, y sub 1, y sub 2, y sub 3, and y sub 4? I'm going to take the numbers I need and put them into my formula. So here we go. So we're about to finish this problem. They all don't take this long, okay? Don't feel like it's going to be forever. It's just the first one we have to find everything. So here we go. We found our x values. Oh my gosh, I just realized I called these y. Change these up. These should be x's. I'm sorry. Sorry. Because I haven't found my heights yet. I just found out where they actually are meeting up on the number line. Okay? So what I found, if I can draw the picture for you guys really quick, or at least kind of show you, right here at this top picture, I figured out this value here, this value there. I figured all those out. Okay? So this was 11 fourths. This was 14 fourths. This was 17 fourths. Like, I just figured out the x values right there. But now I got to find the y values. So the way you find the y values, I told you, you get your x values and you plug them in, right? So let's get my x values here. And I'm going to plug them in to y sub 0. So my x value for the first one was a 2. So f of 2 equals 2. I'm not going to make us do all the work. I'm just going to do this quicker, okay? We're basically plugging it into 3x minus 4. That's all I'm doing. F of 2 is 3 times 2 minus 4. Y sub 1 is f of 11 fourths. I'm plugging in x sub 1 for that one, right? So when I plug it in, I get 4.25. Okay, 4 1/4. To find y sub 2, I plug in x sub 2. So x sub 2 is 14 fourths. Well, my answer comes out to 6.5. That's the height of that left side of the rectangle. Okay, it's 6.5 units. To find y sub 3, I plug in x sub 3, which is 17 over 4. So if I do 3 times 17 over 4 minus 2, I get 8.75. And then to find y sub 4, I plug in x sub 4, which is a 5. Well, 3 times 5 minus 4, that's 15 minus 4, so that's 11. These are my y values. Okay, these are all my y sub 0, y sub 1, y sub 2, y sub 3, and even y sub 4. Even though I don't have to calculate it, those are the numbers. So, to put those into my equation, it's 3/4 times y sub 0, which is 2, plus y sub 1, which is 4.25, plus y sub 2, that's 6.5, plus y sub 3, that's 8.75, and that's where I stop, because remember our formula for the left-hand method stops one number short. So all you have to do is get your calculator, add those numbers together, and multiply them by 3/4, and we get 16.125. So this is saying that the area underneath the curve using a left-hand method is going to be 16.125. Now, again, we're using a left-hand method, okay? A left-hand method. So that means that the graph, I kind of showed it to you guys before, it looks like this. A left-hand method with 4 different cuts would be from 2 to 5. It would be this area right there. Okay, if I zoom in real quick, notice it's an under approximation. Okay, so that means 16.125 is not actually the right amount, it's under the right amount. So let's do the right-hand method. And for that one's going to be a lot quicker because we're going to use all these numbers up here. Okay? All these, we're not even going to use the x side. We're only going to use the y side right now. All right? So here we go. This is part B. Right-hand method. So here's the formula for the right-hand method. The integral from a to b of f of x dx is approximately b minus a over n. Notice that doesn't change, but there is one small change. Instead of starting from the left side, okay, the left side of the rectangle, we're going to start with the right. So in other words, you start with y sub 1 plus y sub 2 plus y sub 3 plus etc. plus y sub n. So this one ignores the first height and actually uses the last height. If I could draw this for you. Again, we're just kind of doing quick sketches here. The idea is this. It's coming this way. Let's say this is 2 here, and we'll say this is 5. We're using the right hand, so the right top side of the rectangle. So if you look, we're over approximating, okay? We're over approximating the area. But here's the nice thing. Didn't I already find out all the y values for this problem earlier? Right? So all I have to do is fill in the information. So the integral from 2 to 5 of 3x minus 4 dx is approximately, remember these are approximations, b minus a over n. What was b minus a over n? 3 over 4. What's my y sub 1? That'd be 4.25, right? Y sub 2, 6.5. Y sub 3, well, that's 8.75. And I have to go all the way up to y sub 4, right? Because that's the n value. So I've done y sub 1, y sub 2, y sub 3, y sub 4, which would be 11. Okay, now if I can, I'm just going to kind of label this. This is y sub 1 plus y sub 2 plus y sub 3 plus y sub 4. So now just add those up and multiply by 3/4, and you get 22.875. So that was quick, right? All you need to know is the formula to use. So the formula is given to you up there. Notice, left-hand method starts with y sub 0. It ends at y sub n minus 1. It ends early. Right-hand method starts later. So it doesn't start with the 0th term. It starts with the first term. And it ends at exactly the nth term. Okay? And all the values, y1, y2, y3, y4, all those values came from the previous work. All right, now we're going to jump to D. Are we okay with this one? So let's jump over to D. Trapezoid. Now, the trapezoid method has a different formula. It's the integral from a to b of f of x dx is approximately b minus a over 2n. Now, for the left and right and the midpoint method, b minus a over n is called our base. This is called our height. Okay, and I'll show you a picture why we call it the height. Okay, and then you're going to multiply by y sub 0 plus twice y sub 1 plus twice y sub 2 plus etc. plus twice y sub n minus 1 plus y sub n. Notice the trapezoid uses everything, but it doubles up in the middle. Now, why does it do that? Let me show you a picture. I'm just going to try, I'm going to draw a picture that's kind of like just the one quadrant, okay? The reason why it does this, let's say the graph looks like this. And we'll start from here. We'll call that A. And we'll call this B. Okay? So if I start drawing trapezoids, I'm going to exaggerate the drawing. It's supposed to be a lot closer, but I'm just trying to show you guys something here. Trying to make a point in a sense. All right. How many times is this highlighted side used for a trapezoid? I don't know if you guys can see. I'll zoom in a little bit. See this side right here? The highlighted side. How many times is it used to build that trapezoid? How many times is it touched? Once, right? What about this side right here? How many times is a trapezoid touching it? Look at both sides. Aren't there two trapezoids touching it? Look at this side. Aren't there two trapezoids touching that side? And there's two touching this side. And there's two touching this side. How many trapezoids touch this last side over here? Only one. Does it make sense why the heights at the very far left and the very far right, look at your equation, say y sub 0, y sub n, but all the heights in the middle, they get touched how many times? Twice. You notice how the equation says that all the middle heights have to be doubled? Okay? Because they're being used 2 times. They're being used twice. But the edges are only used once. Now, what I'm about to highlight right now, isn't that considered the height of the trapezoid, not the base of it? Right? A trapezoid normally will look something like this. This is the height. This is base 1 and base 2. Look at the way I drew it. I'm standing it up. So isn't that considered the height of it, not the base? Right? The bases are actually the sides that are going up. Okay? So that's why the b minus a over 2n is not the base, it's the height. All right? So we are going to have to recalculate the height for this because it's twice n on the bottom. So let's go ahead and do that. So the integral from 2 to 5 of 3x minus 4. By the way, you notice I'm kind of going right into it because we use all the same information we had before. Okay, we still use all that same information. So b minus a over 2n is 5 minus 2 over 2 times 4. Okay, and then just to show you what it should look like, you're going to have y sub 0 plus twice y sub 1 plus twice y sub 2 plus twice y sub 3 plus y sub 4. That's going to be our last one because you go from beginning to end with this equation. Okay, it says from 0 to n according to the definition. All right, so let's start calculating. 5 minus 2 is 3 over 8, so 3/8. Y sub 0 for us is, what is our y sub 0? What's the height of it? You look at your information. Anybody have it? Should be on a list. Isn't it 2? Right, look at the information. Let's go all the way back up here. Y sub 0 is 2. Y sub 1 is 4.25. So let me go back down here. So it's 2 times 4.25. I'm just showing the work, but yeah, I hear you. 2 times, so y sub 2 is 6.5. Plus 2 times y sub 3, that's 8.75. And then y sub 4 is 11. Well, if you calculate this, we're going to get 3/8. 2 plus 4.25 times 2, that's 8.5 plus 13 plus 8.75 times 2, that's 16, 17.5 plus 11, that's equal to 16 point, I'm sorry, not 16. Sorry about that. 19.5. 0, 0, if you want to write that, but. So notice we've had 3 different measurements. The left-hand method, which measured under, gave us 16.125. The right-hand method, which was over, gave us 22.875. And the trapezoid method, which gives us a pretty good approximation, gave us a 19.5. Okay? So I'm going to go ahead and stop here. Let me stop the recording.